Okay, so it's really my pleasure to present some of the work that I'm doing, and I called this presentation Droplets, Change Phase, Droplet Condensation and Evaporation. So why droplets? Well, they're just really everywhere in nature and in a lot of our industrial processes. Definitely rain, but also agriculture. If you think about irrigation, advanced manufacturing now uses a lot of droplet-based techniques. Definitely medicine, biomedical. If you think about DNA assaying, or right now with COVID, we're all familiar with droplets that spread diseases. And really the focus of my work so far has been energy and thermal management, where if we think about electronics cooling or the energy water food nexus of how to optimize processes. So really in order to understand and to use droplets to our advantage, we have to understand the physics behind them, how they interact with surfaces, but also how they interact with each other. And one type of process that droplets are involved in are phase change processes. And probably the oldest and most common and one of the most abundant processes is the natural water cycle, right? We have evaporation from lakes. We also have evaporation from the ocean or from droplets that are sitting on surfaces. And then definitely a droplet mechanism is the condensation in the clouds. The water precipitates, and then we have also evaporation directly from the rainwater. So this is a closed cycle that we find in nature, but also important these days is our phase change processes in power plants or in chemical plants. And on a little bit of a smaller scale in electronics cooling. So the lesson here is that whenever we have evaporation in a closed cycle, we need condensation. So those are intimately coupled. So what my group has been focusing on mostly is combining basic science on phase change heat transfer with some of more applied work on electronics thermal management. I've been looking predominantly at droplets, but not only at droplets. But today's work, obviously, I can't talk about all of the projects that I have. So I'll be focusing on two projects that involve droplets that are situated here in this liquid vapor domain. A little bit about condensation, and then a little bit about evaporation. So we're a thermal community, so we probably all are familiar with condensation. So you need a cold surface and warm vapor. And the first step involves a nucleation. So you have to form a critical mass of your vapor molecules. Once you have the nucleus, you can actually grow the droplet either via direct condensation, or at some point droplets will start coalescing. And when they're big enough, gravity can help remove them. Now, if we look at the heat transfer during condensation, we see here in the red line the fraction of heat transfer. And what we see is that 60% or more than 60% of the heat transfer happens for droplets between 1 and 10 microns. So clearly, this size range of droplets is extremely important to understand and to also enhance, ideally. So we set out to understanding these droplet or this size range of droplets, both from a heat transfer perspective, but also from their dynamics. And the goal is to have high droplet mobility. So we're talking about dropwise condensation instead of filmwise condensation here. We want to avoid flooding. And if we want to really have a high contribution of these small droplets, we need a frequent clearing of nucleation sites. So dropwise condensation has been around for a long time, but the problem has always been that the promoter coatings are really not long-term stable. They blister, they crack, and over a few hours or a few weeks, you convert your dropwise condensation to filmwise condensation. So one approach that has been suggested about 10 years ago was to use lubricant-infused surfaces for heat transfer. It's basically a porous, nanoporous or microporous surface that you infuse with lubricant. In our case, it's an oil. And then droplets are extremely mobile. And it has been shown that you can have sustained dropwise condensation, and these surfaces are also self-repairing. So during my PhD, I started a project that looked at the droplet size distribution of condensing water droplets on the lubricant-infused surfaces with different types of lubricants of different viscosity. And the reason we were interested in this droplet size distribution is that we need that for modeling, for predicting off heat transfer rates. And what we'll see is that it follows fairly well Rose's model for solid hydrophobic surfaces, except for the smaller range of droplets, where our data shows more smaller droplets than what Rose's model down here would predict. And if you remember back, this shaded area here in red, that's the 1 to 10 micron range. So that's really where the majority of heat transfer happens. So the question that we then asked when I moved to WashU to form my own research group is whether there is a fundamental difference in the nucleation dynamics or the dynamics of the small droplets between solid hydrophobic surfaces and the lubricant-infused surfaces. The second question is whether we can actually just shift the entire curve to the left, which would mean more droplets, more smaller droplets, higher heat transfer rates. So in order to understand these small droplets better, we had to take our samples to the microscope. And down here you see a video of just a regular smooth hydrophobic surface. Droplets are fairly stationary because they're small. Your scale bar is 10 microns, and the popping is basically just a coalescence of the droplets. Now, what we see on the lubricant-infused surfaces is extremely different. Notice that the sample was oriented horizontally on a microscope, so it's parallel to gravity, and yet we see extremely high droplet mobility, and the droplets seem to be dancing over the surface, across the surface. So we were puzzled, and we didn't quite understand what was going on here, but clearly this behavior of droplets has to influence heat transfer rates. So we used a slightly different imaging technique to figure out what might be causing this, this droplet dancing. And if we look closely, we can basically see at the beginning of the process, of a condensation process, that we're forming two different types of areas. One is where we have droplet clusters, and then we have, if you see it, a little bit of a darker shaded region. That's where we have a little bit of a thicker oil. And then in between where it's lighter and you see some interference patterns, that is where we have an extremely thin oil layer, so lubricant layer. So we call this oil-rich and oil-poor regions. And what we see if we zoom in a little bit more, and again, you see really nice interference patterns that represent changes in the thickness of the oil, is that droplets really seem to be nucleating primarily in the oil-poor regions, and really almost not at all in the oil-rich regions. So our hypothesis was that we have this redistribution of the oil, and that is what causes this random motion of the droplets. So basically, we have the oil-rich regions around the larger droplets, and where we have fairly high droplet mobility, and then we have the oil-poor regions where we have high nucleation rate but lower droplet mobility. So our hypothesis was that right at the interface between the oil-rich and the oil-poor regions, we form these menisci between droplets, and then we have capillary forces that attract the smaller droplets to larger droplets. And you can see here just a time sequence of two droplets on a surface, not through coalescence, just deposited, but it shows how the capillary forces between the droplets really induce motion. So when we look at the process in a little bit more detail during condensation, indeed we see that smaller droplets seem to be moving towards larger droplets. And if we take our hypothesis and try to model that, so we say we have a small droplet that's in basically sitting in the influence area of a meniscus around a larger droplet, it'll experience the capillary force towards the larger droplet. And then it'll have viscous dissipation, Stokes flow, and other hydrodynamic resistance to its flow towards the larger droplet. And with a very simple force balance, we can model this motion very accurately. And we see here a plot where we have the model and then the 3 data points that we have for 3 different oil viscosities. And we see that model and our data points match very well. So that means that the lower the lubricant viscosity, the higher droplet mobility.
I think Pat is frozen.
But what is special? Oh. Is it just MD who can't hear me?
I can hear you again now, Patty.
Okay,
Yeah,
fabulous.
it is frozen for a moment.
Okay.
Your video is
Okay, but we seem to be good now again. That's good. So what is really exciting about these surfaces is that we have a passive mechanism for drop. Instead.
I think she froze again, right?
Yeah.
So maybe for the interest of communication, we should probably try to
Stop our videos.
stop our videos, yeah.
Let me just go to the next slide. Maybe that helps with unfreezing or with the freezing problem.
Patty, can you come back to the slide before, because we lost your voice.
This one?
Yes, because I completely lost the last explanation about the last part. Sorry for that. No.
The self-propulsion, that we can use this technology in applications where we cannot rely necessarily on gravity to remove droplets from a surface. Now I seem to have lost everyone completely.
Well, Patty, we
We
can
could
hear
still,
you.
yeah.
Ah, okay.
We can hear you. And for personal experience, maybe you have this problem when you have huge videos that are being played. So the problem may disappear when you have slides which are non-animated. But again, I invite everybody to turn off their camera at this point, just for the sake of improving the communication.
Yeah, I'll just go to the next slide because that does not have a video, so that might help as well. So now we have this possibility of potentially enhancing heat transfer through this really rapid motion of the droplets on the surface. But we also have these oil-rich regions which probably prevent nucleation in those areas. If we compare it, for example, to a solid hydrophobic surface without any lubricant, we potentially have less area available for nucleation. And we actually quantified that. So if we look at how much area is available for 2 different oils and we compare it to a solid hydrophobic surface, actually, because we have very high mobility and redistribution of oil for a low viscosity surface, we actually have more area available on average for nucleation than for a regular hydrophobic surface, despite having oil poor and oil rich regions on a surface. At the same time, we also have a lower energy barrier towards nucleation. So that combined, we were interested in quantifying nucleation rates. So what we measured here were 1 micron size droplets and basically the number rate density as a representation of nucleation rates. And what we see is that indeed, as we decrease the viscosity of our lubricant, we get more smaller droplets, which basically relates to a higher nucleation rate and potentially higher heat transfer rates. The only concern that we have is that with a lower viscosity of the lubricant, we might also get a faster degradation of the surfaces. So that's something we still need to look into and understand really in more detail on how lubricant drains during the operation. One common question is, because the lubricant drains from the surface, is do lubricant-infused surfaces really have a potential to be used in applications? For water condensation, maybe not necessarily, because there are other ways we could create and sustain dropwise condensation. But one of the big advantages of lubricant-infused surfaces is the ability to have dropwise condensation for refrigerants and other low surface tension fluids. So that's where I do see potential application for lubricant-infused surfaces for these low surface tension fluids. So moving forward, I just showed you that for the condensation, really what we want is the high droplet mobility. If we're talking about evaporation, actually a low droplet mobility might be better to maximize heat transfer rates. Meaning if we have a pinned droplet, we could potentially increase heat transfer. For example, if you look at two droplets of the same initial volume, one is on a hydrophilic surface, the other is on a hydrophobic surface, we see that the hydrophilic droplet evaporates faster than the hydrophobic droplet. It has a pinned contact line, which means that as the droplet evaporates, the droplet becomes thinner and thinner, and the conduction resistance through the droplet, especially near the contact line, becomes smaller, so we have enhanced heat transfer at the contact line, whereas for the hydrophobic, we typically have a moving contact line, so the contact angle stays the same, and we have a diffusion resistance near the contact line. So if you look down here, we see that actually in both cases, we do have most of the heat transfer happening at the contact line. So here the color code is heat transfer rate. So meaning that if we can pin the contact line and really create a large contact line density, we can potentially increase heat transfer rates. So we wanted to explore basically the overlap between hydrophilic and hydrophobic surfaces. And the way we approached this was by wettability-patterning surfaces. So wettability-patterning has been used to manipulate droplet dynamics on surfaces. And we wanted to not just manipulate the droplet dynamics, so the hydrodynamics, but also the heat transfer. So we created these biphobic surfaces where we have the background here. So the blue is a superhydrophobic surface. And we used UV and ozone exposure with a mask to create local patterns on the surface that are hydrophobic. So the contact angle is around 90 degrees, but they're sticky. So they still have the structure, the underlying structure of the superhydrophobic surface, just that the chemistry has changed slightly. So they become sticky in a Weisensee state, basically. And we use optical and IR imaging to quantify the droplet dynamics and how the heat transfer is coupled to those. So if we look just at a regular droplet on a horizontal surface, because we have a superhydrophobic matrix, but pinning at the basically transition area between the two wettability patterns, we start with a droplet with a very high contact angle, and we end with a droplet with a very small contact angle, but the base area remains the same. So that allows us to really normalize the heat transfer rates that we're measuring. The bottom left shows the temperature distribution, the bottom right shows the heat flux. And what we see is very similar to what we would expect, is that we have a high heat flux around the contact line of the droplet, and the center is basically doesn't contribute to heat transfer at all. So that is what we expected from previous studies as well. Now, because we have the sticky hydrophobic part center, we can actually take our sample and just flip it 90 degrees and look at evaporation on a vertical surface. And the first thing that we notice is that our evaporation of the same droplet volume was actually 10% faster. So that was the first puzzling result that we found here. The second is that you'll see, especially here in these two plots, is that we have a non-symmetric temperature distribution. So the bottom of the droplet is colder than the top of the droplet, and we also have a higher heat flux at the bottom of the droplet than at the top of the droplet. Now, of course, we have a hydrodynamic asymmetry as well. The contact angle on the top is roughly 90. Contact angle on the bottom is much greater than 90. I'll skip this slide. So with the different contact angles, what we would actually expect is that at the bottom we would have the big diffusion resistance, so we would have a lower heat transfer. At the bottom we should have evaporative, at the top we should have evaporative cooling and a lower temperature. So exactly we would expect the exact opposite of what we're actually observing. So we observe the bottom being colder and having a higher heat transfer, and the bottom warmer and a lower heat transfer. And the solution to this apparent contradiction is the internal flow. So we have actually this circulation within the droplet that forms a big one big vortex, and it transfers cold fluid from the apex towards the base of the substrate, and that's why we're getting a colder temperature at the bottom. And overall, this one big vortex is really what helps us increase the overall heat transfer and contribute to this 10% faster evaporation rate. Now my computer shows me that my internet connection is unstable. Can you guys still hear me though?
Yeah.
Yes.
Okay, cool, perfect. So we wanted to take this idea of the wettability patterning one step further, and we looked at droplet impact dynamics on a wettability pattern surface, and the dynamics themselves, the spreading especially, looks very similar to a regular superhydrophobic surface, but then upon receding, we form these satellite droplets. And our idea is that we can mitigate flooding by having most of the substrate superhydrophobic, so repelling the bulk of the droplets, but creating these satellite droplets that can still enhance heat transfer once the major part of the droplet is gone. So if we look at the IR signature here, we actually see very nicely this formation of satellite droplets that clearly contribute to heat transfer. So if we quantify that, again, we're now creating basically a higher degree of contact lines, a higher density of contact lines. So we would expect a higher heat transfer rates for these additional contact lines that we're creating through the sticky spots and the satellite droplets. Well, that was the theory that we had, or our hypothesis. If we compare it to a superhydrophobic surface, definitely that's the result that we have. So superhydrophobic has the highest average temperatures, the lowest average heat transfer rate, and the pattern surface performs slightly better. Now, if we compare that to just a sticky hydrophobic surface, that actually has the best heat transfer performance. Our idea was that the sticky hydrophobic, for a single droplet, it has the better heat transfer performance. But once you're talking about multiple droplets, if you have a sticky hydrophobic surface, you're running the risk of flooding your surface and losing any contact line, and with that eventually losing the advantageous heat transfer performance. Whereas the pattern surfaces, you could mitigate flooding through getting rid of majority of the droplets and just having the small satellite droplets that still contribute to evaporation. Now we did some of these experiments with multiple droplets, but so far our results were fairly inconclusive. So we can't quite say yet whether this is really an approach that has a potential to help with heat transfer rates, especially if we're talking about spray cooling with very fine droplets. This really remains to be seen and remains to be studied. Another aspect that we notice is where we definitely still need to spend some time on is the very central region of the droplet, we saw an elevated temperature and a minimum in the heat transfer rate. And there are basically two options of where that might come from. One explanation is that we have in the center, we have impalement due to a 𝗗𝗃𝗽𝗲 transition, basically due to the hammer pressure in the impact zone, where we breach the superhydrophobic state and we form a local basically wet spot. But that would mean that we had a larger contact area, which would usually mean a higher heat transfer rate, not a lower one. So that's an unlikely explanation. The other one is that we have a bubble entrapment during the impact, where a gas bubble in the center would act like an insulator and lead to lower heat transfer and higher temperature. Now, the droplet is fairly small compared to the entire droplet. So maybe the effect on the overall heat transfer is not super critical, and we're actually working the numbers out right now. Where it is critical, though, is if you're talking not about cooling applications, but the inverse, where, for example, you're thinking about icing, or even more importantly, inkjet printing or additive manufacturing, for example, with metal or with polymers, where you do not want a central bubble that has a different cooling rate or phase change rate eventually than the surrounding droplet, because that would create sites where you create defects. So we want to be able to mitigate this effect of the central bubble where we see a very different heat transfer rate. So that is a project that that we basically just started, that is very much ongoing, where we do see a very small, if we look at heat transfer versus time, a very small difference between bubble and no bubble case on a local basis, but long term, it really doesn't matter whether the bubble is there or not for a cooling perspective. But again, if we're thinking a little bit out of the box from just the thermal management perspective, but looking more, for example, into additive manufacturing, this will become very important to look more into. So with that, I'd like to thank Nenad and Bill King at Illinois and the other collaborators there. Without them, obviously, I wouldn't even have started with any of these projects. But I also want to thank my collaborators and my students and postdoc at WashU. We all know that without our students, there is no research going on. So especially Jingxing Sun, Wenliang, they really did, and Vivek did the work that I showed today. NSF is right now funding the work on the lubricant-infused surfaces. And the evaporation basically was funded through my startup.